Good morning everyone. So welcome back to Vidyamandir online classes. So here this is Venkat sir. So today we are going to teach optical isomerism. Optical isomerism is one kind of stereoisomerism. In the last part of the video we already discussed what is stereoisomerism and types of stereoisomerism. Under the stereoisomerism we discussed in detail about geometrical isomerism. So the second kind of stereoisomerism, that is what? Optical isomerism. Is what are optical isomers and how can we distinguish the given compound is optically active or inactive. So let us go in detail. So first of all, optical isomers. So optical isomers are nothing but the compounds having same molecular formula, same structure as well, but differ in their optical activity. And that compounds we call it as what? Optical isomers, and that phenomenon is called what? Optical isomerism. Now, optical activity. What do you mean the optical activity? See, suppose you take a sample solution. If you pass plain polarized light, PPL, we will discuss what is a PPL, we will discuss later. If you irradiate the PPL into this solution, if the PPL light is coming out, exit with same angle as like how we irradiated, with the same angle, if the PPL is coming out, then that compound is optically inactive. Suppose if you irradiate the PPL light into the sample solution, if that light, PPL light, plain polarized light, if it is bending either into right hand side or into left hand side, if it bends with a certain angle, then that compound is what? Optically active. Specifically, if the PPL light is bending towards right hand side, then that compounds we call it as dextro-rotatory. If they bend to the left hand side, then that is what? Levo-rotatory. So simply called D, and this is what? L. Okay. So likewise, based upon the bending of the PPL light, if they won't bend, optically inactive. If they bend either to the right hand side or left hand side, then that compound is optically active. So this phenomenon is called optical activity. So, and that compounds which are having the difference in their optical activity, that compounds we call it as what? Optical isomers. Okay. Now, this optical activity or optical isomerism we can explain in two approaches. So one is experimentally proof, means an experimental approach. Next one, theoretical approach. So first of all, let us discuss experimental approach. So by doing experiment, how can we distinguish the compound into optically active and inactive? Let us see. So in this experimental approach, the instrument that we use to distinguish this, we call it as what? Polarimeter. So in this polarimeter, if you see the structure of this polarimeter, there was a light source. So light source means generally the radiations are coming in all the directions. Okay, so this means these light radiations are going in all the directions. Okay, so this is a normal light So that normal light I am indicating with different directions. Now when you irradiate this light into nickel prism, what happened? This nickel prism will filter all these radiations into only one direction. That means after we irradiate into that, the light will come out with the same plane like this. Okay, and that light, the radiations is having the same plane, that light we call it as what? Plane polarized light. Simply we call it as PPL. Okay, so plane polarized light is nothing but the light radiations, all the light radiations are having the same plane, then that light we call it as a plane polarized light. Whereas the normal incandescent light, where the light radiations are having different planes. That is the difference between normal light and plane polarized light. Now, when you irradiate this plane polarized light into the sample solution, here I am taking this is what? Polarimetric tube. Polarimeter tube. So in this polarimetric tube, we will take the sample solution, the compound whose optical activity we need to calculate, that you prepare with a solvent and make a solution, and that solution you take it in this polarimetric tube. So when you irradiate this plane polarized light into this polarimetric tube, and remember that the sample solution, the concentration of this solution should be expressed in gram per ml. The concentration should express in which units? Gram per ml. And the length of this tube should be expressed in decimeters. So these two units we should maintain. So remember this in case of polarimetric tube. Now after we irradiate the PPL into the sample solution, if the light comes out with the same angle as like how we irradiated, in the same wise, if they come out without any reflections or deflections, then this is what? Optically inactive. Optically inactive. Suppose if this light is bending to either right hand side or left hand side. So two possibilities here. So this is one possibility. Okay, another one is what? So understood. Here this plane polarized light is bending to right hand side and bending to left hand side. So if they bend to any other directions, then that compound is what? Optically active. And I already told you, if the PPL bends to right hand side, this is what? Dextrorotatory. If it bends to left hand side, this is what? Levorotatory. Okay, and this angle, with what angle they are deflecting, this is what? Theta. We represent this with a theta. That is what? Angle of reflection. Angle of reflection. By using that angle of reflection, we can calculate specific rotation of this compound. Okay, so we have a formula. What is that? The specific rotation. Specific rotation. We represent this with alpha. Specific rotation alpha is equal to observed angle of rotation. Observed angle of rotation. What we observe, that is what? Theta. Observed angle of rotation divided by concentration of the solution. Whatever the solution that we have taken, that concentration. Concentration should be expressed in grams per ml. Concentration C into length of the polarimetric tube, that is expressed in decimeters. So by using this formula, that is alpha is equal to theta by C into L. By using this formula, we can calculate what? Specific rotation of the given compound. So this is what? Experimentally proof, experimental approach. So experimentally, how can we conclude the given compound is optically active or inactive? Simply you prepare the solution, you take that solution in the polarimetric tube, irradiate the plane polarized light. If they won't bend, if they exit with the same angle of rotation, that is optically inactive. If they bend with a certain angle, okay, then that is optically active. Okay, so by using this formula, that is specific rotation alpha is equal to theta by C into L. By using this formula, we can calculate the specific rotation of the given compound. But remember that the specific rotation of the compound is specific and unique for a particular compound. All compounds are not having the same specific rotation, they are having different specific rotation, and that's a fixed value. Okay, so remember that point. So this is about experimental approach of optical activity. Next, move on to the theoretical approach of optical isomerism. So in order to explain theoretically, so the compound should fulfill the two conditions. After they fulfill the two conditions, then we can decide the given compound is optically active or inactive. Let us see the conditions required. The conditions required to show the optical activity. The first condition is the given compound should be dissymmetric, should be chiral molecule. Chiral molecule. When we can call it as a chiral molecule, when the molecule is dissymmetric, then we call that molecule as chiral molecule. What do you mean by the dissymmetric? This means not showing. It should not show the following two symmetries. So one is plane of symmetry. It should not show the plane of symmetry. And the second one is center of symmetry. If these two symmetries are not there, then we call that molecule as a dissymmetric, also called what? Chiral molecule. Okay, we will discuss what is the plane of symmetry, center of symmetry later. Next, the second condition is the compound should have, or the molecule should have at least one chiral center. So the chiral center also we call it as asymmetrical center or asymmetric carbon. The chiral carbon or chiral center also called asymmetrical center or asymmetrical carbon. What do you mean by the chiral center or asymmetrical carbon? When we call, if the carbon attaches to, as we know, the carbon is a tetravalence, it can be bonded with 4 other groups. If the carbon is attached to 4 different groups, A, B, C, D, all are 4 different groups, then this carbon we call it as asymmetrical carbon, also called chiral carbon. So the second condition required to show this optical activity is the molecule should have at least one chiral carbon. Suppose the compound is not having chiral carbon, then no doubt that is optically inactive. Okay, to be active, to be optically active, that molecule should have at least one chiral center. It can have more than one also, it's not a problem, but compulsory they should have minimum of one chiral center. So these are the two conditions. So after they fulfill these two conditions, definitely that compound will be optically active. Now let us see what is plane of symmetry and what is center of symmetry. So let us see. The first one, plane of symmetry, I am writing as POS, plane of symmetry. So it is nothing but it is an imaginary line, an imaginary plane which divides the given molecule or compound into 2 equal halves. Then that imaginary plane we call it as what? Plane of symmetry. So for example, you take square. Okay, so to this square, okay, how many plane of symmetries are there? So this is one plane of symmetry. This is another plane of symmetry. And this is what? Another plane of symmetry. So this is another plane of symmetry. Likewise, so many planes of symmetries are there. So plane of symmetry is nothing but an imaginary plane which divides the given molecule into two equal halves. Then that imaginary plane we call it as what? Plane of symmetry. For example, I am taking a compound here. Likewise, I have taken. Now tell me, is this compound having plane of symmetry or not? So obviously, we generally think that if we cut this, there was no two equal halves. But remember that it should have at least one plane of symmetry is enough. One plane of symmetry is enough. See that CH3 I am writing as carbon, hydrogen, hydrogen, hydrogen. Now tell me, if we cut this molecule in this plane, we are getting two equal halves, right? So this compound is having plane of symmetry, no doubt. And one more thing, if this compound CH3, CH3. Now tell me, as we know, wedge dash notations. So this is wedge notation. This bond indicates what? That molecule, that this group is above the plane, and this dash notation indicates below the plane. Okay, now, so if you consider this is a 1, 2, 3, 4. This is on the same plane. One group is above, another one is below. Right? If we cut this molecule in this axis, are we getting two equal halves? No. So no way. If we cut this molecule in this way, okay, so this is above and this is below. We are not getting two equal halves. So this compound is not having plane of symmetry. Okay, so likewise, we can differentiate the given compound having whether they are having plane of symmetry or not. So this is about the plane of symmetry. Next one, center of symmetry. Center of symmetry I am representing with COS. Center of symmetry. Yes, what is the center of symmetry? Center of symmetry is nothing but say line which is passing through the center. That line should pass through the center of the molecule. That's the first condition. The second condition is, suppose if there was two similar groups are there, both the groups should be opposite to each other. Whenever the two similar groups are opposite and also equidistant from the center. Equidistant from the center. When they fulfill these three conditions, definitely that compound is having center of symmetry. So first one is that line, that imaginary line should go through center of the molecule. The second one is what? The two similar groups. The two similar groups are opposite to each other. Opposite to each other. The third one is that both groups are equidistant from center. So when they fulfill these three, then that compound is having center of symmetry. Let us apply this. I am applying this to this compound. See that is this compound having center of symmetry or not? Let us see. First of all, this is the center of this compound. Okay, so first one, you just take any line which is passing through the center. So I am taking this line only. Okay, and the two groups should be opposite. Now tell me, is this compound is obeying the second rule? They are not opposite, right? Suppose the same group is here, then they both are opposite. So it is not fulfilling the second condition. So there was no center of symmetry to this compound. Now I will give you one more compound. Now tell me, is this compound having center of symmetry or not? See, this is the center and the two groups are opposite to each other and also equidistant. How far this group is from the center, the same distance this group is also present. So definitely this compound having center of symmetry. So this is about the center of symmetry. When the compound is not having any one of these, the compound should not have plane of symmetry and also center of symmetry, then only that compound will be optically active according to the first condition. What is the first condition? The given compound should be chiral. Chiral means dissymmetric. Dissymmetric means they should not have any kind of plane of symmetry or center of symmetry. At least one symmetry if they have, then definitely that compound is optically inactive. Okay, now to understand this well, okay, we should know about configurations, R and S configuration. What is R configuration? What is S configuration? And based upon the RS configurations, how can we differentiate the given compounds into enantiomers, diastereomers, identical, meso, racemic mixture, these all things. Okay. Okay. Now, in lactic acid and tartaric acids, okay, how many of chiral centers are there? Let us see. Thereafter, we will move to the RS configurations. So, if you take the lactic acid structure. So this is lactic acid structure. Lactic acid. See that carbon, and here the place where the two lines are crossing. This is a vertical line, this is a horizontal line. The place where the two lines are crossing, that there one carbon is there. Remember that. Okay. So carbon, carbon, carbon. Total 3 carbons are there. Now, is this carbon is a chiral center? No way. Second one, check this. This carbon is a chiral carbon, or asymmetrical carbon. Why? Because left side hydrogen, right side OH, top COOH, bottom CH3. 4 different groups are present. So this carbon is what? Chiral carbon. To differentiate that, I am representing this with asterisk. It means this is a chiral carbon. So similarly, tartaric acid if you take COOH, HOH, HOH, COOH. Now in this compound, first compound, fourth compound, these two are not, first carbon, fourth carbon, they are not chiral centers. Check the second and the third. So if you take this one hydrogen, OH, COOH, and this entire group is fourth group. Okay, so this is one chiral center. Similarly, this is also one more chiral centers. So likewise, here one chiral center is there. Here 2 chiral centers are there. Likewise, we can count the number of chiral centers. Next, let us we move to the RS configuration. So this is also we called as absolute configurations. So in this configuration, R stands for retro, S stands for sinistro. Retro and sinistro. And this configuration is based on CIP rules. In the last part of the video, we discussed what are CIP, Kohn-Ingold Prelog rules. Kohn-Ingold Prelog rules. These rules we follow to identify the priority of the given compound, given groups. So as we just briefly I am telling, order of priority is directly proportional to atomic number. In case of isotopes, order of priority is directly proportional to atomic mass of the given isotope. In case of groups, order of priority is directly proportional to atomic number of first attached atom. Suppose if the first attached atoms are same, in case of similar first attached atom, then move on to next attached atom likewise. So these are the some rules that we follow to identify the priority of the groups present attached on the carbon. Now, R stands for retro, S stands for sinistro. Now, I'll just give you the hint. By following this hint, you can easily differentiate the given carbon. This carbon is having retro configuration or sinistro configuration. So what is that? Just after you give the priority to the 4 groups, first by following the SIP rules, you give priority to the 4 groups. After you give the priority, if the fourth priority group is last priority, fourth priority means last priority. If the fourth priority group is at bottom or top, whatever it may be. This is a vertical line. If the fourth priority group is on vertical line, remember that, vertical line, if the priority sequence follows clockwise, if the priority sequence follows clockwise, then this compound is retro. If the priority sequence follows anti-clockwise, then that is what? Sinistro. So once again, if the least priority group is on vertical line means either top or bottom, vertical line. If the order of priority following clockwise direction, then that is retro, anti-clockwise direction, that is sinistro. Suppose if the fourth priority group, least priority group is on horizontal line, either left side or right side, whatever it may be. If the order of priority follows clockwise, that is sinistro. If it is anti-clockwise, that is retro. So this hint helps you a lot to identify the configuration at a particular chiral carbon. I'm just applying the same logic to this one. See that. COOH I have taken. HOH, CH3. This is one, and it's a mirror image. What is its mirror image? OH left side, hydrogen right side, and CH3. Now we need to differentiate which is R configuration, which is S configuration. See that, first of all, follow the SIP rules and give the priority to the four groups. See, here carbon attached, oxygen attached, carbon attached, hydrogen attached. Which is having highest atomic number? Oxygen. So oxygen containing group, there is a OH group gets first priority. Next, carbon groups. Carbon containing two groups are present, CH3 and COOH. If first attached atom is the same, then move on to the next attached atom. In this group, carbon next attached to O, but here hydrogen. O is having highest atomic number. So this COOH group is having second priority. And the remaining CH3 group is getting third priority, and the fourth one is hydrogen. Likewise, by following SIP rules, give the priority first. After you give the priority, check the least priority group, hydrogen. Where it is? It is in the horizontal line. If it is in the horizontal line, this one, horizontal line, clockwise is sinistro, anti-clockwise is retro. Now, horizontal line. Now, come from first priority, 1, next 2, next 3. That means it is going in anti-clockwise. The priority, order of priority is going in anti-clockwise. 1, 2, 3. Anti-clockwise. If it is anti-clockwise, what is that? Retro. So the first compound is retro configuration. Next, move on to the second compound. So first, second, third, fourth. Here also fourth priority group is in horizontal line. Now starts from 1. 1, 2, 3. That means it is going in clockwise. Clockwise means this is S configuration. So likewise, we can easily give the configurations to the given compound. So once again, one more example I am going to take, that is a tartaric acid. COOH, HOH, HOH, COOH. Here how many chiral centers are there? 1 and 2. This is one chiral center, this is another chiral center. 2 chiral centers are there. Okay, and you can do the numbering from top to bottom or bottom to top. Both are same. Why? Because the two terminal end groups are same. In case of two terminal groups, in case of similar terminal groups, you can start giving the numbering from any one of the side, no problem. So 1, 2, 3, 4 or 1, 2, 3, 4. Now I'm giving the numbering from 1 to 4, top to bottom. Now at second carbon, let us see. First priority, second priority, third priority and fourth priority. You may get the doubt. Here carbon, here also carbon. Carbon attached to O, here also carbon attached to O. But see, double bond O is there. If there was a presence of multiple bonds, then that multiple bond containing group will get the first priority. That is why this group is getting higher priority than this group. So, first priority, second priority, and this entire group is getting third priority, and this is fourth priority. Fourth priority group is in a horizontal line. Then, and order of priority anti-clockwise. In case of horizontal line, anti-clockwise is what? Red. Anti-clockwise is red. So, at second carbon, which configuration? 2R configuration. Now, third carbon, you let us see. First priority, second priority, third priority. 1, 2, and this entire group is 3 and 4. Now, fourth priority horizontal line, 1, 2, 3. Again, clockwise. Clockwise is what? Sinister. So, 3S. If we give the numbering from top to bottom, this is what 2R 3S configuration. Suppose if we give the numbering from bottom to top, then 1, 2, 3, 4. In that case, 2S 3R will come. 2S 3R will come. So in case of similar terminal groups, RS and SR both are same. Okay, they both are identical. Okay, we will discuss that later. Okay, anyhow, so this is likewise by following the SIP rules and this hint is very important. By following this trick, you can easily differentiate the configuration of the chiral carbons. Now I am drawing all optical isomers of tartaric acid, and I am trying to give the relation between the isomers. So first of all, tartaric acid. So the four isomers, that is COOH, HOH, HOH. This is the first compound. The next compound, write the mirror image of this. OH, hydrogen, hydrogen. Clear? This is the second compound. Next, third compound. You keep the first compound as it is. Third carbon position you change. OH, H. Second carbon position HOH, but third carbon alternated. So this is third compound. And the fourth one, now you change at the second carbon, that is OH, H. Keep the third carbon as it is. Then this is what? Fourth compound. So these are the four possibilities of tartaric acid. Okay, four possibilities. See, after we draw the all four possibilities, you give the configurations to all. So in the previously we did. So this is what 2R 3S. So this is 2R 3S. Okay, now coming to here. This is 2S and 3R. 2S 3R. Next one more thing. If you give the numbering from top to bottom, this is 2R 3S. If you give the numbering from bottom to top, what will be? This is 2S 3R. 2S, this is anyhow, this is R, this is S. If you give the numbering from top to bottom, 2R 3S. If you give the numbering from bottom to top, 2S or 3R. Both are same. Next one. So this is what? S and this is R. So if you give the numbering from top to bottom, 2S or 3R. If you give the numbering from bottom to top, 2R 3S will come. 2R 3S. See that first compound, second compound, you check that 2R 3S. This is also 2R 3S. The configuration as second alternate 2S to 3R, 2S to 3R. The configurations remains same. For the first two compounds, the configurations are remains same. So the first two compounds we call it as what? Identical isomers. The first component, second component, they both are same. If they are identical, no need to draw two structures. You can take any one of these two structures. Okay, no need to consider two structures, only one is enough. So that is why I am removing the first compound. So the total optical isomers for this compound, 3 only, not 4. Okay, now So understood why we are eliminating the first compound. First compound, second compound, both are identical. If they are identical, one structure is enough. That is why I eliminated the second. Clear? Now, if you check the second and the third, now you give me configurations. By following the trick, I am directly giving RISSR. Okay, you don't be confused. Here this is what R, and this is R, and this is S, this is S. So what is the configurations? Even if you give from top to bottom or bottom to top, this is always 2R, 3R. Even this is what? 2S, 3S. Okay, now the compound 2, 3. The compound 2 and the compound 3. You check the configurations. This is a 2S, 3R. This is a 2R, 3R. Okay, so the set of compounds is a 2, 3. This set, this pair of compounds, and also 2, 4. 2, 4. That's it. How many total? 2, 3, 2, 4. This pair of compounds, this pair and this pair of compounds we call it as diastereomers. Diastereomers. We will discuss what is diastereomers. We will discuss. Don't be worried. So the pair of compounds is a 2, 3 and 2, 4. They both are diastereomers. Next one. You compare the third compound and fourth compound. The fourth compound is a mirror image of third compound. Okay, the fourth compound is a mirror image of third compound. So, if the stereoisomer, if the pair of compounds which are mirror images to each other, then that pair of compounds we call it as what? Enantiomers. So, the compound 3 and 4, this pair are what we call enantiomers. We call enantiomers. So, enantiomers are nothing but the stereoisomers which are mirror images to each other. Which are mirror images to each other. Just imagine our two palms, right palm, left palm. If you keep like this, one palm is a mirror image of another palm. That means these two palms, this pair of palms, what we can call enantiomers. We can call. And one more definition is also there. The pair of mirror images, these two are mirror images, which are non-superimposable to each other. Non-superimposable. What is the meaning of non-superimposability and superimposability? Suppose this is a one image and it's a mirror image. If you keep the mirror image as it is, are they coinciding? No. That means they both are non-superimposable mirror images. Suppose if you keep the mirror image and if they are coinciding like that, they are superimposable mirror images. Now our two palms are non-superimposable mirror images. So this is the best example for enantiomers. Now the compound 3 and compound 4 are mirror images. But if you keep the fourth compound and third compound, they both are not coinciding. That is why third and fourth compounds are enantiomers. So this is about the tartaric acid and the diastereomers, enantiomers. Now let us explain about relations. So what are the relations we are going to study in this stereochemistry? So the first of all, already we discussed about enantiomers. When we call them as enantiomers, the stereoisomers which are mirror images to each other, that stereoisomers we call it as what? Enantiomers. The stereoisomers which are mirror images to each other. Then you may get the doubt. The compound 1 and the compound 2 are also mirror images. Then why don't we call the first two compounds as enantiomers? You may get the doubt. See that here they both are mirror images, no doubt, but their configurations also same. Here 2R3S, here also 2R3S. But enantiomers, this is 2R3R, but this is 2S3S, opposite configurations. Okay, you don't think that all mirror images are enantiomers. okay, the two mirror images whose configurations are opposite to each other, okay, then that pair of isomers only we called as enantiomers. Here example, a set of third compound and fourth compound. Here third and fourth, this is a pair of enantiomers. Next one, and if you see the properties of enantiomers, the enantiomers having the same molecular formula, okay, and their physical properties are different. Sorry, their physical properties are almost same. Physical properties are almost same, except they differ in their what? Optical activity. Here this is a 2R 3R, but this is what? 2S 3S. Okay, the pair of isomers whose physical properties are almost similar, but they are differ in their what? Optical activity. Next one, diastereomers. Diastereomers. Yes, I told you diastereomers example 2, 3, 2, 4. These are the two sets of diastereomers. How can we say that these are diastereomers? See, diastereomers are nothing but a pair of stereoisomers which are not mirror images to each other. See that second compound, third compound, is they both are mirror images? No. If any two compounds which are not mirror images, then they are what? Diastereomers. That is why 2, 3, one set is diastereomer. Similarly 2 and 4, these two compounds also not mirror images. So how can we define the diastereomers? The stereoisomers which are not mirror images to each other. Mirror images to each other. And one more difference, enantiomers are showing the similar physical property, but diastereomers shows different physical property. So we can easily separate the diastereomers from mixture. Okay, so this is about the diastereomers. Here in the given above example, 2, 3, this is one pair of diastereomer. 2, 4, this is another pair of diastereomer. And also 1, 3, 1, 4. Okay, 1 and 2 both are identical. That is why I am not giving 1, 3, 1, 4 combination. Okay. Next one, identical isomers. So I told you, compound 1 and compound 2, they both are identical. How can we define? So it's nothing but a pair of compounds having the same molecular formula and also same configuration. Even their stereochemistry also same. Then that pair of isomers we call it as what? Identical isomers. Okay. So the pair of compounds having same structure or same IUPAC name, their IUPAC name is same, and also stereochemistry also same. Then that pair of isomers we call it as identical isomers. Next, identical isomers are showing almost same physical and their optical activity also same. Next, an important, meso compounds. Meso compounds. So what are meso compounds? Very, very important. And remember that meso compounds are optically inactive. Meso compounds are optically inactive. So why they are optically inactive? Let us see. After you understood what are meso compound, you can easily understand. So first of all, meso compound is nothing but, I will give you an example. So this is the best example for meso compound. See that meso compound is nothing but a compound in which half part, see above part and below part, one half is a mirror image of another half. Okay, one half is a mirror image of another half. Then that compound we call it as what? Meso compound. So one half is mirror image of another. Then that compound we call it as meso compound. Why the meso compounds are optically inactive? See that I told you the first conditions required to show the optical activity. What is that? They should not have any kind of plane of symmetry or center of symmetry. But here see that this is a plane of symmetry only, na? So one half is a mirror image of another half, means it has clear plane of symmetry. If it has plane of symmetry, definitely it is an optically inactive. That is one reason. And one more reason is, so if you see the structure, this is what sinistro and this is retro. So what do you mean the S? S means it rotates the plane polarizer light to left side. R means right side, means half body bending the PPL into left side. Another half body is bending the PPL into right side with equal magnitudes. So finally both will be cancelled together. Ultimate final result is what? 0. That is why the meso compounds are optically inactive because of two reasons. One is because of the presence of internal or interior plane of symmetry. Interior plane of symmetry. The second reason is because of internal compensation. Half body, how much the half body is compensating, and in the same way opposite compensation is given by another half. So it's very, very important. So the meso compounds are optically inactive because of one is interior plane of symmetry. The second one is internal compensation. Internal compensation. So this is about the meso compound. Remember that meso compounds are optically inactive. Next, racemic mixture. So what is a racemic mixture? The name itself, it's a mixture. Okay, racemic mixture is nothing but the mixture of compounds. So both dextro compounds and as well as levo compounds, both are present. And one more thing, racemic mixture is also optically inactive. Okay, meso compounds and as well as racemic mixtures, both are optically inactive. Just imagine a compound, this is dextromer, and another compound, this is what? Levo. Now I am mixing both, and in this compound both dextro, levo, both are present. Okay, what the dextro compound will do? It rotates the PPL into right side. What the levo compound will do? It rotates the PPL into left side. Okay, at a certain point of time, the total magnitude of left side is equal to total magnitude of right side. So overall it becomes what? 0. So this is called, this D plus L mixture we call it as what? Racemic mixture. Racemic mixture. And this phenomena of making racemic mixture by adding both the isomers in a particular composition. You don't think that equal amounts. Okay, no need. Equal amounts, no need. Sometimes 50-50 ratio, sometimes 40-60 ratio, sometimes 30-70 ratio also, the compensation will be 0. Okay, why? Because dextro, it is bending the light into with the angle of 60. Levo is bending with the angle of 45 degrees. Okay, so with this no need of equal magnitudes. Clear? So that is why no need of equal compensation. At a particular compensation, this mixture becomes what? Inactive, optically inactive. And that process of preparation of racemic mixture by adding certain components and certain ratio of dextro and levo, we call it as what? Racemization. The process of preparation of racemic mixture by mixing dextro and levo compounds, we call it as what? Racemization. And the reverse process is what we call it as, that is what? Racemization, and that is isolation. Okay, isolation. So opposite process. So this is about the racemic mixtures. Now let us we take the two compounds. By looking at their configurations, let us we give the relation between the two compounds. This is a compound 1 and this is compound 2. And these two compounds are having only one chiral center. So how many of chiral centers? Chiral centers 1. Having chiral centers 1. The first compound having R. The second compound is also having R. Two compounds having the same configuration, what we call identical. Similarly, S, S, identical. So this pair of compounds are what? Identical. Next, if it is R and this is S, opposite configuration. If it is S and the second compound is R, what we call? These are what? Enantiomers. Enantiomers. Understood? Having the chiral centers only one. R, S, S are identical. R, S, S, R are enantiomers. Now take two chiral centers. Number of chiral centers are 2. The first compound having R configuration. So first, second carbon, third carbon, R configuration. The second compound is also having R configuration. Then what we call? Identical. SS, SS, identical. RS, RS, identical. SR, SR, identical. So they are what? Identical isomers. Now, RR, SS, SS, RR, RS, SR, SR, RS. Now tell me what are these all? These all are what? Opposite to the second compound having opposite configuration to the first compound. So these all are what? Enantiomers. Enantiomers. Now diastereomers. First compound is having RR, second compound having RS. RR, if it is SS enantiomer, RR identical, but this is what? RS. They are not mirror images first of all. Similarly, SS, RS, RR, RS, so already over, SR. So these all are what? Diastereomers. Diastereomers. So by comparing the two compounds, we can differentiate them into identical enantiomers and diastereomers. So best way. Next one. How to count the number of optical isomers? Optically active isomers, optically inactive isomers. How to count? So I just give you the formulas as like how we calculate the geometrical isomers in case of polyenes. Similarly, even this compounds also, by knowing the number of chiral centers, we can calculate the number of optical isomers, number of optically inactive isomers, and number of meso compounds we can calculate. Let us see. Counting the number of optical isomers. So the first case, the case 1, that is two similar terminal ends. Okay, the first case we will follow when similar terminal ends. Both the terminal ends are same. For example, tartaric acid you take. COOH is COOH. Terminal ends are same. That is the first condition. And here N indicates number of chiral centers. N indicates what? Number of chiral centers. So when they fulfill these two, then the formula number of optical isomers. Number of optical isomers formula 2 power n. 2 power n. Number of optical isomers are what? Sorry. This is not similar m, dissimilar m. Dissimilar. If the two terminals are different and having n number of chiral centers, this is the formula. Okay, next, second case. Case 2. If terminal ends are same, having n number of chiral centers, and this n value is even. N number of chiral centers. How many of chiral centers? 2, 4, 6, 8, 10. Likewise, even number of chiral centers if they have. Best example, tartaric acid. See that tartaric acid is COOH. Two terminal ends are same. And how many of chiral centers are there? 2 chiral centers are there. So in that case, number of optical isomers, optically active isomers. See, optical isomers are different, optically active isomers are present, different. Optical isomers means total number of isomers, we call it as optical isomers. In that isomers, a few are optically active, few are optically inactive. So, the total number of optically active isomers is equal to 2 power n minus 1. 2 power n minus 1. Next, the total number of meso compounds. Meso compounds means optically inactive. No? The total number of meso compounds is equal to 2 power n by 2 minus 1. 2 power n by 2 minus 1. So this is optically active formula. This is optically inactive formula. Now the total number of optical isomers is equal to sum of both. So if you add both, that is 2 power n minus 1 plus 2 power n by 2 minus 1. By using this formula we can calculate. So apply for tartaric acid. N value is what? 2. So number of optically active isomer 2 power 2 minus 1 is 2 power 1, 2. 2 power 1, that is 2 optically active isomers are there. Only 2 are there. Next, see that, and meso compound, number of meso compounds 2 power n by 2 minus 1. N means 2 here. 2 by 2, 1. 1 minus 1, 0. Anything to the power of 0 is 1. Okay. Next, total number of isomers 2 plus 1, total 3 are there. I told you 1, 2, 3, 4. 1, 2, both are identical. So you take 1. So total number of optical isomers are 3. Out of 3, 1 is a meso compound. Remaining 2 are what? Optically active compounds. Okay. So this is about similar terminals having even number of chiral centers. Next, third case. Case 3. Similar terminals. So their terminal ends are same and having n number of chiral centers. N number of, and that is odd. Okay. Then the formula, number of optically active isomers. Number of optically active isomers formula 2 power n minus 1 and plus 2 power n minus 1 by 2. So this is the formula for total number of optically active isomers. Next one, so this is minus 2 power n minus 1 minus 2 power n minus 1 by 2. By using this formula, we can calculate total number of optically active isomers. Next, number of meso compounds. Number of meso compounds means total number of optically inactive compounds is equal to 2 power n minus 1 by 2. Now, the total number of optical isomers is equal to sum of both. If you add both here minus term and this one, both will be cancelled. Finally, we will get the formula 2 power n minus 1. So just slight changes in case of third compared to the second. Number of optically active isomers are 2 power n minus 1 minus 2 power n minus 1 by 2. Number of meso compounds is 2 power n minus 1 by 2. And total number of isomers is equal to 2 power n minus 1. You take any example and by applying that example in this case, we can easily get the number of optical active and inactive and total number of optical isomers. So this is about the optical isomerism. If you have any doubt, just ping me in the WhatsApp. I will help you out. Okay. Thank you.